My presentation is not so long because it's actually the story about the start of the research. So just to take a pointer. We are now, I will speak a little bit about application of different weather forecasted product in the crop modeling and in this case in the plant disease prediction. So our story with weather forecast applications started with crop modeling. We had some research published in that field, and then we thought, let's go back 10 years when we had some first models in this field and try to use those models and to see what weather forecast is going to give us. So that was the primer idea, and our focus was actually to go a lot forward and to try to think operationally and to try to connect with forecasting and warning service of Serbia with their knowledge and to combine our knowledge from meteorology and their knowledge from plant protection. And as we spoke about time series data that we can produce, and we spoke about differences of time level data. So the first plan was to use short-term weather forecast in plant prediction, and then to see what of other forecasted data we can use. Because nowadays there are a lot of generated and produced forecasted data on the monthly season and seasonal season for 7 months. Of course, we need to think about the problem because the diseases are something that are happening in next 5 days, for example, 10 days. So monthly forecast can give us prediction of the risk. Is the following month going to be risky or not so much? Or if we are speaking about seasonal forecast, then we can also speak only about the risk. But if we go down, if we go to 4-day or 3-day or 5-day or maybe 2-week forecast, then we can use it together with plant disease model. And if we want to be successful in this field, we need first of all a lot of field observations. So meteorological observation, plant phenological status, and also disease appearance and disease intensity. Of course, all these observations are sometimes difficult to collect because we have a lot of spraying. There is no treatment-less field, so if the disease is already evolving, that means that there are some problems with management practice. So it is actually difficult to collect disease appearance data, and there is just a small amount of them, but we hope that there will be something for us there. And we also need to have good calibrated model. For our purposes, we are now using empirical plant disease models, but we are hoping to go further to have some dynamical models introduced as well. And of course, if we want to go further to look in the future, we need numerical weather prediction model outputs. So the first step was to run numerical weather prediction model. And because this was the results that are created during this project, we got in the collaboration with our supervisor on the first summer school. She taught us how to run a WRF-RV model, and we used GFS input data and produced 4x4 forecasted for 2015 and 2016. And later on used those outputs to run biometeorological Bacchus model. This is a model developed by researchers from Faculty of Agriculture with collaboration of plant pathologists. And it consists now of 3 diseases. One of them is Plasmopara victicola, the only medium of wine grape that we have chosen to see what results we are going to develop at the end. And model is actually consists of 3 parts. We have input files that are meteorological and biological things. Modeling part that is so the middle, or the modeling module, how we can call it, it's the numeric mathematical part of the whole model, where all empirical relations are introduced in. For Plasmopara, we have inside famous 310 rule for spraying. In the case of Serbia, this 310 rule is a little bit moved up because the temperature, base temperature for this disease should be 10 degrees. In Serbia condition is 12 degrees. So 12 degrees of temperature in 2 days, above 12 degrees. 10 millimeters of precipitation in 2 days, and if shots of wine grapes are 10 centimeters, then we can assume that infection will start. Also, incubation period of this disease is calculated by Miller's curve, and at the end we can produce data that are saying when the primary, secondary, or subsecondary infection is going to appear, and when the incubation period is going to end. So we got some data from the field for 2016, in both years for just one location, and here I have plotted observed precipitation amount and predicted one, as well as temperature. So disease is triggered by temperature and the precipitation. That is why only these data are presented. And you can see that in both cases, when we calculated with modeled and with observed meteorology, we got infection on start of the infection on 13th of May in 2016. Observed data showed that the infection, primary infection, incubation period was ended on 23rd of May, and we got prediction and observed, or actually calculated values of with predicted meteorology and with observed meteorology only in 2 days apart. So we got the results here. On the other location, in other year, we ran a model with observed meteorology as well as with forecast, and we got the same infection start on 26th of May, and in this case also we got 2 days apart of predicted and observed, and observation on the field showed that primary infection was observed on 4th June in 2015. So these results were very promising for us. Unfortunately, we didn't have a lot of observed. Unfortunately for us, great for producers, we didn't have a lot of data from the field in this period, but we hope that we will maybe manage something. And later on, I will speak a little bit. I'm now entering the collaboration part, since these are the results from Converis project that Professor Eitzinger is going to speak about tomorrow. They provided us with field observations from these locations. I'm not sure what are the names now, but you can see a lot of locations. and meteorology together with disease appearance observation. And we run our model to see what we are going to get. First, we didn't get anything because our temperature limit was 12 degrees. Then we needed to go down, and we got to 10 degrees. So it was exact 310 rule for Austria. And you can see that time of first infection was, in every case, very, very near one to another. So 1 day difference. And when we calculated incubation period, end of incubation period, we also got very nice results for all locations. The next here graph is just for one location in Austria, because the data that they have provided us are continuous observations. So we got the data. So here in red line you can see the incubation and every second infection afterwards, the start at the end, but it is expressed in percentage. Our calculation are not presented in percentage, so I couldn't calculate these lines. So you can see just start and the end, but also you can see how close we have been to every second or third or fourth period after. And we have done this for every location for Austria, and the results were very promising. Promising enough for Professor Eitzinger so that he can introduce this plasmaphora calculation into their system. And we hope that we will have now, we have done something with gridded data, and now we hope that it will go online for Austria in future months. Yeah.
But it has to be tested.
Yeah, of course. We are just hoping. Yeah. So, in the future, we are planning to use Bacchus in all for other two diseases, and to see what we'll get with monthly forecast, seasonal not so much, but we can run it to see how it look like. And one day to have operational system, and to introduce pest algorithms as well. Since I'll talk about mosquito, we are hoping to place that kind of algorithm in some other pests that are problematic in agriculture, and to see what we are going to get in the end. So thank you for your attention.